Okay, we talked about this yesterday in the lab, but let's see, you got the matrix 0.9, 0.2, 0.1, 0.8 multiplied by SD equals a multiple of SD, and the multiplier we're going to call lambda, and that's going to be our eigenvalue, okay? Now this is what we did. I'm going to do the whole thing again briefly, okay? So if I multiply 0.9, 0.2 by SD, I get 0.9S plus 0.2D. So you multiply row by column. Everybody okay with that? Mm-hmm. And if I multiply 0.1, 0.8 times SD, I get 0.1S plus 0.8D. And that's going to equal, well, if I multiply lambda by SD, we haven't really defined this, but it seems reasonable, and it's so that the multiplication kind of distributes, okay? So we get this system of equations, right? Well, we get this matrix equation. This matrix equation means, well, if these things are equal, that means this must equal this, and this must equal this. Otherwise, it wouldn't be equal. So 0.9S plus 0.2D equals lambda S, and 0.1S plus 0.8D equals lambda D. Now, we rearrange this very easily. We get 0.9S minus lambda S plus 0.2D equals 0. And we get 0.1S plus 0.8D minus lambda D equals 0. And now we factor out the S, and we get 0.9 minus lambda times S plus 0.2D equals 0, and 0.1S plus 0.8 minus lambda D equals 0. And that is just the system. 0.9 minus lambda, 0.8, 0.1, that's 0.2, not 0.8. 0.8 minus lambda times SD equals 0. Okay? Now, we could easily prove it, but we're not going to. So you accept that there are three variables, lambda S D, only two equations, right? Okay? But
you know what all the bases are that are allowed, right? Not one, okay? But there are a couple of bases that were.
we can solve this provided this determinant is 0. Okay? So we get lambda squared minus 1.7 lambda plus 0.7 equals 0. Because that says that the determinant of this is 0. That's our characteristic equation, right? And you've seen that you can just write this equation. You just write this out. You've got to say determinant and use the notation for Wolfram alpha. But Wolfram alpha will then solve it without ever having to expand it, right? Now you can always do determinant of this and you'll get this, okay? But you know, you get all the information if you run through the examples that you were doing yesterday, okay? And I assume everybody has, so you know what I'm talking about. Now, that's how this condition connects to the characteristic equation and gives you your eigenvalues. And in this case, lambda equals 1, or lambda equals 0.7, and then you get the eigenvectors. Okay? And I'll complete that. Okay? If lambda equals 1, then our first equation here
One other law that gets used.
and I'll label these now 1,
Another one that gets used is natural.
2. So from 1 over here,
Natural law is a right? And it is written as Ln. Notice the near and the rubber blow. I can't remember which way it is. Rubber blow, your L will put in the cheese button.
this is what you get. You plug lambda in, plug 1 in for lambda, and you find S equals 2D. Okay? Where does S equal 2D? Along a line that looks like this. So any vector along this line, this vector or this vector, any vector along that line is an eigenvector. Okay? Excel or Wolfram alpha tells you that vector. You got to choose one, so it chooses 2, 1. You could have chosen 2 million, 1 million, and yeah, okay. Could have chose 0.02, 0.01. Okay. Any vector where this is double this is an eigenvector. And when you plug that vector in here, if S is equal to 2D, you're going to get 1 times whatever SD is. Okay? Then, if lambda is 0.7, you get 0.9 minus 0.7 S plus 0.2D equals 0. S solve for D. D equals negative S. And the picture of that is along this line. Any vector along this line is an eigenvector. Okay? And any vector along this line, when you apply the transformation, gives you a vector parallel to it, but 7/10 as long, 70% of the length. So if you have a vector here and apply the transformation, it'll shorten it to this.